Hello students, today we will discuss about Demorgan's theorem. See, in the digital electronics, till now we discuss about the different types of gates as well as the different types of number conversions and the Boolean algebra. Now what about the Demorgan's theorem? Demorgan's theorem represents the two of the most powerful laws in Boolean algebra. There are two laws of the Demorgan's theorems. Means first is the first law of the Demorgan's theorem states that the complement of a sum of variables is equal to the product of their individual complements. Let us see how we write about the statement of this theorem. You see the logic equation first. The first theorem having the logic equation, here you see on the LHS side a plus b bar, here you see a plus b bar equal to a bar dot b bar. Now how we can understood this, or how we can remember this easily? You see here a plus b bar is on LHS side, output is a bar dot b bar. How we can remember? So see here a plus b bar, if you cut the line from here, see here we cut the line here and we change the sign here, so we will directly get output as a bar dot b bar on RHS side. So the first theorem of the De Morgan states that a plus b bar whole bar is equal to a bar dot b bar, means the complement of a sum of variable equal to the product of their individual complement. That is the statement, and this is the symbol, this is the logical equation of the De Morgan's first theorem. Now we can see which are the symbols, logic diagrams. So here you see in this figure a plus b, here you see this is the a plus b. You know, before this theory, different types of gates. So this is known as the OR gate. A plus b is OR gate. If we want to draw the symbol of NOR gate, we have to add another gate as a NOT gate after OR gate. So we directly get the output as a NOR gate. So here this is known as the NOR gate. So simply we can see that here, see the equation, logical equation of the a plus b bar here. So this is a plus b bar. So this is the final output of a plus b bar here. Now the RHS side. What is about the RHS side? RHS side, it is known as a bar dot b bar. So a bar means we are using NOT gate here. So again we see here this is the NOT gate, and this one is the another NOT gate as a, this is for a bar and this is for b bar. So a bar dot b bar, here you see a bar dot b bar. So RHS is the equation, a bar dot b bar is the output. You can simply write here, instead of NOT gate you can simply draw the bubble here, and for another input you can also draw bubble here. So this is known as a bar dot b bar. So the first theorem states that a plus b bar equal to a bar dot b bar, means this is a plus b bar and this is the logic symbol of a bar dot b bar. Now we will see the truth table of this theorem. First of all, we have to give input as a, there are two variables, so we write a, then b, then a plus b, and then a plus b bar. So for LHS side, you see here a is 0, b is 0, then a plus b you already know, the simply binary addition is a plus b, it is 0. But what about a plus b bar? It is the complement of a plus b, so it is known as 1, means the output is 0, the complement of the output is 1. So the first result is, whenever we apply 0 plus 0, the output will be 0, but due to the De Morgan's theorem, the LHS side, a plus b bar is taken, it is known as 1. See here in the first. Then in second, this is known as 0 1, means a is 0 and b is 1. So we simply say that 0 plus 1 is equal to 1. Here you see 0 plus 1 is equal to 1, but the output is a plus b bar. So we have to complement the 1, so it is known as 0. The third line is shows that a is 1, b is 0. So 1 plus 0 is known as 1. So if you simply we can see this is known as 1, but its complement is 0. So it is very easily understood. And the fourth is a is 1 and b is also 1. The output will be 1. So here we simplify the output as a 1 and a plus b bar is 0. So this is the total LHS side. Now what about the RHS side? You see here RHS is known as a bar dot b bar. So simply whenever we want to see the output or we have to conclude the output, we have to give the input as a, then b, then a bar, we required a bar, then b bar, and then the product of a bar and b bar. So first of all, in the first row you see here we will take a 0, a as a 0, b as a 0. So you see that a is 0, so a bar is 1, b is 0, then b bar is 1. Again in the second, a is 0, then a bar is 1, b is 1, then b bar is 0. In third row, a is 1, b is 0. So a is 1, then a bar is 0, and b is 0, then b bar is 1. Means simply if 1 is there, then complement will be 0, and 0 is there, the complement will be 1. That is a simple NOT equation. Then a is 1, you see here a bar is 0, b is 1, then b bar is 0. So these are the simple 4 different types of calculation. Now final equation is a bar dot b bar. So for the first, a bar dot b bar, 1 into 1, you see 1 into 1 is known as 1. Then 1 into 0, 1 into 0 is known as 0, simple multiplication method. 0 into 1 is known as again 0, so it is again the multiplication method, and you know 0 into 0 is 0. So this is the fourth row. So you see that here in the last columns of this LHS as well as RHS, here in this a plus b bar as well as a bar dot b bar, you see here the output of a plus b bar is 1 0 0 0. You see 1 0 0 0, and this is LHS side, and the output of the RHS side is again 1 0 0 0. So we simply said that LHS equal to RHS. So in general we see here the law can be extended if there are more than 2 inputs, then you have to simply write a bar plus b bar plus c bar plus d bar, and the RHS side you have to cut the line and change the sign like a bar dot b bar dot c bar dot d bar, like that. So this is the first theorem of Demorgan. Now students, we see about the second law of Demorgan's. So in the second law what happens, we have to simply change the sign in the LHS side. So instead of a plus b bar, we have to write a bar a dot b whole bar. So the second law of Demorgan's theorem states that the complement of product, here you see this is the product, a dot b is the product, and complement means the bar is given on the top of that product. So we simply say that the complement of the product of variable, means here we are using 2 variable, is equal to the sum of their individual complements. So a dot b bar is equal to a bar plus b bar. This is the second law of Demorgan's theorem. Now we will see how we draw the logic diagram. You see here the first logic diagram means LHS side, a dot b bar, you know This is the symbol of AND gate. AND gate symbol, you know. And if we want to show it as a NAND gate, A dot B bar is known as NAND gate. So AND, invert of AND is known as NAND. So we have to keep the NOT gate at the output of AND. So it is simply known as NAND gate. You can easily draw the simple symbol of the NAND gate is like this, A dot B bar. Now RHS side. You see here the two inputs A bar plus B bar. Here it is A, then A bar is, by using NOT gate we will get A bar. The second variable is B. By using this NOT gate you get output as a B bar here. So the output of A bar plus B bar, for the ORing we are using OR gate here, so it is known as A bar plus B bar. You can simply write that, or the draw about the RHS side is known as A bar as a simple bubble, B bar as a simple bubble here also, then the output will be A bar plus B bar. So this is the simple drawing logic gate of the RHS side. Now you see the truth table. On the LHS side, you see, first of all the output is A dot B bar for the LHS side. So first you have to take A as a first variable, B as a second variable, and the product of that two is A dot B, and finally A dot B bar. So again you have to write, or you have to keep the input as a 0, then 0 as a input. The product of that two is again 0, but here you see in the final column A dot B bar means it is the complement of A dot B. So here if A dot B is 0, the output is A dot B bar, means it is 1. Now the second input A is 0 and B is 1. So here you see A dot B is 1 into 0, it is known as 0, but the output is complement of 0, it is 1. The third row is A is 1, B is 0. The product of 1 and 0 is 0, and the output is 0. But here we see A dot B bar is there, so it is the complement of 0, it is known as 1. The final row A is 1 and B is 1, though the product of this both is 1, 1 into 1 is equal to 1, but here we have to complement the 1, so it is known as A dot B bar is equal to 0. So this is very simple multiplication method. Now RHS side. RHS side we have to conclude A bar plus B bar. What will be the output of A bar plus B bar? But first of all we have to write the first column as A, second as a B, third as a bar, fourth as a B bar, and final output is the addition of A bar plus B bar, means third and fourth column. Now first of all we keep A as a 1, A as a 0, B as a 0, again A as 0 and B as 0, if both are 0, but whenever we keep A as 0, then A bar will be 1. Whenever we keep B is equal to 0, then B bar is 1. So it is very simple, we have to complement the both of the variables. Again A is 0, then A bar is 1 here, B is 1, then B bar is 0. I will dot it about the red colors. A is 1, then A bar is 0, B is 0, then B bar is 1. Again A is 1, then A bar is 0, B is 1, the B bar is 0. So it is very simple method of the NOT gate. Now we will add the third and fourth column, A bar plus B bar. So simply we can see 1 plus 1. Here you say 1 plus 1. 1 plus 1 means output is known as 1. Again 1 plus 0. It gives output as a 1. Again 0 plus 1. It gives output as a 1. And 0 plus 0, the output is a 0. So you see here again, like the Demorgan's first theorem, the LHS equal to RHS. Here you see LHS is for the last column here, A bar dot B bar. See here, A bar dot B bar, the output is 1110. The RHS side you see here, A bar plus B bar is also again 1 1 1 and 0. So we can conclude that LHS equal to RHS. So the second law of this Demorgan states that the A dot B dot B dot C dot D dot D means if we have so many variables, then at the output end there will be a line is cut and sign is to be changed. This shows the NAND gate equivalent. So these are the two different theorems you can understood easily. Now we will see the example based on the Demorgan's theorem. The first simple example is we have different 4 variables. Here see the example. Apply Demorgan's theorem for the following expression. Y is equal to A plus B bar dot C bar plus D whole bar. You see here, this is the whole bar. So how can we simplify this? So in the theorem you see that the whole bar is, first of all we have to cut here from here you have to cut, and we have to change the sign at here also. So the second statement, output will be A plus B bar whole bar. We have to change this sign from dot to plus here. So A plus B whole bar, A plus B bar whole bar equal to C bar plus D whole bar. Okay. Now we will apply again the Demorgan theorem here in this step. Here you see this is A bar, first one is known as A bar dot B double bar. Here actually A bar we have to change cut the line from here we cut the line and change the sign here. So A bar dot, here you will see there will be B double bar. So B double bar, you know, it is known as B. So we simply write A bar dot B here. Then what about C bar plus D whole bar? Again we have to apply the Demorgan's theorem. You see here C double bar, so it is easily get output as a C. Then cut the line here, so and then D bar, so C bar dot D bar. So simply we can write the final equation is A bar into B plus C into D bar. So by this example we can simply learn about if any type of Demorgan theorem may present in front of you, where that type of sum is available in front of you, you can easily solve the problem. Okay, so I may conclude that you may understood the different types of Demorgan's theorem and the example based on it. Thank you.